Hi, this is Mr. Mack. This is the second of the videos about the normal curve or the standard normal curve. Now, in the first video, I showed you the standard normal curve. We talked about the empirical formula. We talked about standard deviations. Now, what happens is many times we have two scores or achievements or something like this from different groups, and the question is which one is better or which one is more significant. And the way we do that is we evaluate how many standard deviations away from the mean each of those events are. And here's an example. In the women's heptathlon in the Olympics, there are 200-meter and 800-meter runs and the 100-meter high hurdles, shot put, javelin, etc. Somehow the performances in all 7 events have to be combined into one score. How can performances in all 7 events be compared? They do not even have the same units. The races are recorded in seconds, throwing and jumping events are in meters. The best 800-meter time run by Gertrude Bacher of Italy was 8 seconds faster than the mean. The winning long jump by the Russian Yelena Prokhorova was 60 centimeters longer than the mean. Which deserves more points? Now, as it says here, the trick is comparing these very different looking values by using standard deviations. So let's go down here and actually, okay, let's just stop for a minute here. And this formula right here is the one that actually takes raw scores. Now, raw scores are just scores that come to us and converts them into a standardized score. See, and what we do is we take the raw score, x, minus the mean, and so this value is how far away from the mean we are, and then we divide by sigma. Sigma is a symbol for the standard deviation, and so that tells us how many standard deviations there are in the distance between the raw score and the mean. So that converts a raw score to a standardized score, and the standardized score basically is the number of standard deviations away from the mean. Now, so back to our question. Now, the winning time of 129 seconds was 8 seconds faster than the mean of 137 seconds, and the standard deviation of the qualifying teams was 5.0. So Bacher's z-score, I'm just going to put z sub b, is going to be equal to 129 minus 137 over 5. Now, 129 minus 137 is, well, what is it? It's negative 8. So we get negative 8 over 5, which is negative 1.6. So Bacher's score was 1.6 standard deviations below the mean. And here, below the mean is better. Now, Prokhorova's winning jump was 60 centimeters longer than the average 6-meter jump. The standard deviation was 30 centimeters. So Prokhorova's z-score was 60 centimeters. See, that's you know, her jump must have been 6.6 meters minus 6 meters, which would have been the average. So we get 0.6 if we're doing it in meters, divided by a standard deviation of 0.3 meters, so we get 2. So Prokhorova's long jump was 2 standard deviations above the mean. And so since, well, I forgot the name, Bacher's winning time in the 800 meters was 1.6 standard deviations away from the mean, and Prokhorova's winning long jump was 2 standard deviations away from the mean, we would say that Prokhorova's performance was better than Bacher's. Okay. Now, some general observations. Observations larger than mu are positive. Now, mu is the mean. Sometimes we use the symbol X bar as well. Observations to the right or that are larger than the mean are positive, and observations that are below the mean are considered negative. And I'm back. Let's see, I think what we were saying was that on the standard normal curve, you find that observations that are larger than the mean have positive z-values. Observations that are smaller than the mean have negative z-values, because if you have the observation minus the mean, if the mean is bigger, you get a negative number. If the mean is smaller than the observation, you get a positive number, and the standard deviation is a positive number. Also, I think I said this in the earlier video, the area under the entire curve is 1. Also with that, the curve is symmetric around the average or the mean. So there's 50% of the area is above the mean and 50% of the area is below the mean. Now let's kind of go ahead and do some examples here. Scores on the Wechsler Adult Intelligence Scale are approximately normally distributed for age groups. For 20 to 34, the mean is 110 and the standard deviation is 25. For the 60 to 64 age group, the mean is 90 and the standard deviation is 25. Now, if Sarah's 29, that means she's in the 20 to 34 group. Her mother's 62, so she's in the 60 to 64 group. Sarah scores 135 on the Wechsler, while her mother, Anne, scores 120. Did they say that Sarah's mother was named Anne? I must have missed that. I think we have to assume that that's the case, because they told us Sarah's age, and they told us her mother's age, and then they talk about Anne, so I think we have to connect mother with Anne. Let's do that. Okay, who has the better score? Okay, now Sarah's score is 135, so her z-score of Sarah is 135 minus 110 over 25. Now 135 minus 110 is 25. 25 over 25 is 1. So Sarah is 1 standard deviation above the mean. Now Anne's z-score is 120 minus, what was the mean for that group? It was 90. Standard deviation is the same, 25. So 120 minus 90 is 30 over 25, which is 6/5, which is 1 1/5, or 1.2. So actually Anne did better than Sarah. Now you try. You might want to pause the video here. Okay, it's nice that you're back. Let's do these. The heights of young women are approximately normal, with 64.5 inches and for the mean and 2.5 inches for the standard deviation. Find the standardized height of a young woman that is 68 inches tall and then someone 60 inches tall, and interpret your results. Okay, the z-score for 68 is going to be 68 minus 64.5 divided by 2.5. Now I'm just going to call up the calculator and actually do that on the calculator. I get, in parentheses, 68 minus 64.5. Oops, that's not a point. 0.5 divide 2.5 and enter. We get 1.4. Now, a 60-inch tall person, so that's going to be 60 minus 64.5 over 2.5, and that gives us negative 1.8. So the z of someone with a height of 60 is going to be negative 1.8. Now, it says interpret your results. Well, the results are that someone who's 68 inches tall, a woman that's 68 inches tall, is 1 4/10 standard deviations above the mean. And someone who's 60 inches tall is 1 8/10 or 1 4/5 standard deviations below the mean. So the 68-inch person is taller than the 60-inch person. I'm not sure what else we could do to interpret the results, okay? So suppose instead of looking at just the height of one woman, we wanted to know what proportion of all women were less than 68 inches. Standardizing rescues us again. To do this, we're going to need to use the table. Now, we have the empirical rule, but that only works if the standard deviations are whole numbers. In other words, 1 standard deviation, 2 standard deviations, 3 standard deviations. But now we're dealing with things like 1.4 standard deviations or negative 1.8 standard deviations. To do this, we need to look at the table that represents the area under the normal curve. Now, on the next couple of pages, you have these tables, and I have them right over here on the next 2 pages here. So what we're going to do is we're going to go back and we're going to grab, we're going to deal with this one right here. In other words, we're going to find out the area below 1.4 standard deviations. So we go over to the table, and 1.4 is in the second one here. So we go down to 1.4, and notice these top numbers that you see up here are actually the next number in after the 0.4. So if we had 1.41, for example, we'd be in the second column. But since we have 1.4, or really 1.40, this is the value from the table for that. Now that's 0.9192. Now let's take a look at this, actually the chart's on the previous page. Look at the chart. See, now 1.4 is actually over here someplace. And what it gave us was, I think it was 0.92, I've forgotten it already. 0.9192, okay. 0.9192. So the area to the left of that, all of this area here is 0.9192. Now, if we look at negative 1.8, that's on this page here, negative 1.8, and again, that's negative 1.80. Let's use the green here. Negative 1.8 is 0.0359. So if we went up here and used this table, if this was negative 1.8, then the area in gray here would be, oh gosh, I've forgotten already. 0.0359. Now, what that means is the area between these two lines, let's use blue here, the area between this line and this line, this area in here would be 0.9192, because that's the area from here all the way down, minus 0.0359, which is the area from here the rest of the way down. And so, I don't know, I think maybe a calculator is indicated on this one. So we would say 0.9192 minus 0.0359, and we'd get 0.8833. 0.8833. So 88 1/3% of women would fall between, oops, it's over here. Let's go back here to where we are. It says we want the proportion of all women. So the proportion of all women that fall between 60 and 68 inches would be 0.8833, or 88.33% of all women will be somewhere between 60 inches tall and 68 inches tall. Now, Ms. Weaver has put in here some suggestions as to how to do this. To calculate, how do you read the standard normal table? First of all, calculate the z-scores to 2 decimal places using the formula. Then go to the table and scan down the z column for the whole number in the tenths, and then go across the table for the hundredths. Yeah, that's this one. And the number in the body of the table is the probability for the area to the left of that z value. In other words, it's everything from that value all the way to negative infinity, all right? Although most of it's somewhere between that and -3 standard deviations. And if you want an area between two, you take the larger area minus the smaller area, and you get the area between those two. Okay, so examples. Using the table of standard normal probabilities, find the proportion of observations from a standard normal distribution that satisfies each of the following statements. In each case, sketch the standard normal curve and shade the area under the curve that is the answer to the question. You should really probably do that even before you go to the table. See, now z is less than -1.5. The z-score for the mean is 0, so -1.51 would be somewhere around here. And if we want z to be less than that, we're picking these values over here. So this is the area we want. And that's exactly the area the table's going to give us. So when we go over here to -1.51, here's -1.5, and then we go over to -1.51, we get 0.0655. So the answer to this is this region right here is 0.0655. B, -1.5 is less than z is less than 0.82. Now, we already have the 0.0655 here. This time, what we're looking for is, here's the mean, here's -1.51, and here is 0.082, and we want the area in between these two. Now, we already know that this area is 0.0655 right here, 0.0655. Now, from 0.082 all down, 0.082 is here, 0.7939. So the area from here on down is 0.7939. So the area in the middle, the area between the two, is going to be 0.7939 minus 0.0655. And again, I'm going to go ahead and ask the calculator to tell me what that is. And so I get, what do I get? 0.7939 minus 0.0655. 0.7284. So the answer to this one would be 0.7284. All right, let's just put this down here out of the way. The area to the right of z equals 1.42. So once again, the standard normal curve looks like this. And here is 1.42, and we want this area here. Now, if you look at this, if we look in the table, what we're going to get is this area here. So to get the area we want, we would take 1 from that value. So 1.42 becomes, what does it become? 1.4012, 0.9222. So we go back here. This one is 0.9222. So the area we want is 1 minus 0.9222, and that's equal to 0.0778. So let's just 0.0778 is right there. Okay, now we want the area to the left of z is equal to negative 0.39. So if z is equal to negative 0.39, and we want the area to the left, I went the wrong way there, negative 0.39. Well, now here's negative 0.30. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0.3483. Back, we get 0.3483 for this one. The area between negative 1.2 and negative 0.5. Okay, first of all, I didn't shade this one, so here we go. Like this, here's the mean, and here's negative 0.39, and what we've got is 0.3483 to the left of that value. That's this region right here. Okay, area between negative 1.22 and negative 0.5. Okay, now here's the standard normal curve. Here's the mean. Here's negative 1.22. Doesn't really matter where you put it, except it's got to be on the left of the mean. And the negative 0.5 has to be to the right of negative 1.22, but to the left of the mean. And we're looking for this region here. So now we go to negative 1.22. I lost my circle. Here it is over here. Negative 1.2012. So I get 0.1112. I think I can remember that. Let's go back anyway. So from here on down, we have 0.1112. Now the other one is negative. Oh, that was 1.22, right? So it'll be from there. Now negative 0.5. So we go back to negative 0.5, and that would be right here, 0.3085. So from here on over is 0.3085. So the shaded region would be 0.3085 minus 0.1112, which is going to be a 3, a 7, a 9, and a 1, 0.1973. All right, I'm going to stop this video and start another one with example 2.